Perfect, Aidan. So whenever you're ready.
Okay. Hi everyone, I'm Aidan and I study mechanical engineering in UCD. So last year when we went into lockdown, all my labs were cancelled with no alternative. So the opportunity for us students to have enhanced experiential learning was challenged. While these mechanical experiments are difficult and expensive to conduct, they can be supplemented by digital experiments in a virtual learning environment. Therefore, for my final year project, I set out to study the use of video game physics for digital labs to simulate and investigate nonlinear and chaotic dynamics. But what is nonlinear dynamics? So dynamic systems are those that change over time. In a linear system, the principle of superposition can be applied, meaning that the response of the system to multiple stimulus is equal to the sum of the response to each individual stimulus. But in nonlinear dynamics, this is not the case, which makes it more complicated. Nonlinear dynamics is a concept that is becoming increasingly important. This is because of the rising use of flexible structures in engineering, which have dynamic and nonlinear operational conditions. For example, these mechanics would be particularly relevant in floating offshore wind turbines and soft robotics. These are two technologies which are arguably the future of engineering. So engineers need to know about nonlinear and chaotic dynamics to ensure reliable and safe operation of these systems. But these dynamics are not on the undergraduate engineer syllabus. A core reason behind this is the lack of an experiential approach to nonlinear concepts. My project aims then to solve this by exploring a wide range of nonlinear and chaotic systems that are reduced to the simplest form for teaching purposes. Chaos can be demonstrated with small and simple tabletop toys, which I simulated with the animation software Blender. Blender is primarily an animation software for making films, but to make these films, sometimes fast and reasonably accurate physics simulations is needed. To do this, Blender uses an open source deterministic physics engine called Bullet. What deterministic means is that there is no randomness involved. A deterministic model always ends up the same way if the initial state is the same, just like in real life. The power of the Bullet physics engine comes in its speed of computation. A study showed that Bullet was up to 1,000 times faster than conventional simulation, while still being accurate enough to study particles in geotechnical engineering. So if Bullet is the engine that makes it work, Blender is the driving seat, steering wheel, and gear shifter. Blender is the environments through which you can conduct the simulation. And this is great because compared to proper simulation software like ANSYS, the Blender interface is intuitive and easy to use. This is a time lapse of me creating a simulation of the chaotic double pendulum. In real time, this took me about 6 minutes. The parameters to be set are quite straightforward, and the graphical interface is easy to navigate, especially if you're already familiar with CAD. You can move around and manipulate the bodies easily, and calculating the simulation is also very fast, which you'll see around now. So why am I using these tools to simulate toys? It's because studies have shown that toys can reflect real-world engineering constraints such as location and budget. The toys can integrate design and engineering knowledge to facilitate learning and implement the same educational principles as labs. One study found that in the same university, students who learned with such toys performed better on traditional exams compared to students that didn't. The toys I simulate will be used to demonstrate and study chaos. But what is chaos? While there is currently no robust definition, chaos is characterized by being deterministic and unpredictable, meaning that while all the physics and equations of motion may be known, after some time the system's output cannot be realistically predicted, and this is due to its extreme sensitivity to initial conditions. Chaos is important because it only occurs in nonlinear systems. So this key characteristic here is why a deterministic simulation engine like Bullets is needed. The double pendulum is a classic example of a chaotic system. This simulation shows that even though each double pendulum starts off the same way, infinitesimal differences in the initial conditions led to vastly different outcomes after some time. This is the butterfly effect, an extreme sensitivity to initial conditions. I also simulated other nonlinear systems that appear to be chaotic. This one is called the Spaceballs toy, which has an inner pendulum connected at a 45-degree angle to the outer pendulum, which is made to move periodically. This 45-degree connection combines with magnets that interact with the inner pendulum to make the system nonlinear. And we also have the magnetic pendulum, which is essentially a regular pendulum that is hanging above 3 repulsive magnets that apply nonlinear forcing to the pendulum bob. The motion paths of these systems can be exported to a spreadsheet from which I can analyze in MATLAB. The motion path is sampled every 1,000th of a second. From this, I can calculate the velocity and acceleration for a given point in time. From the positions and velocities, I can plot phase planes. What phase planes are planes in which each dimension is a state variable of the system. State variables are those that are used to completely define the state of the system. So for this system, we can let our state variables be the x, y, and z coordinates of the pendulum and the respective components of velocity. In other words, we can completely define the state of the system at a given point in time from its displacement vector and velocity vector. So nonlinear and chaotic dynamic theory state for a nonlinear periodic system, the phase plane would show a curve that starts and ends in the same place. A chaotic system would fill up an area on the phase plane, and both of these trajectories are able to cross themselves because they're nonlinear. That's the nonlinear and chaotic dynamic theory, but what do we get when we plotted these phase planes using the results from Blender? Well, we got what the theory suggested. The periodic simple pendulum's phase plane is a closed curve. It ends where it started. The nonlinear chaotic system of the magnetic pendulum crosses itself repeatedly, and you can see it's definitely filling up some area on the phase plane. There are some parts of the theory that the phase planes didn't follow. For example, the theory states that a chaotic system wouldn't have a closed curve, but some of these phase planes do show closed curves. However, this could simply imply that the system is nonlinear but not chaotic. But phase planes alone are not sufficient to make this conclusion. To get a more robust conclusion, we can modify this method with Poincaré maps. These Poincaré maps are sections of phase space that are sampled by cutting the phase plane trajectory with a plane. Where these phase space trajectories intersect the plane, we can plot on our Poincaré map, but we only sample it when the trajectory is going into one side of the plane, but not the other side. These Poincaré maps would be used to identify chaos, as chaotic trajectories would form unorganized points on the plane. In chaotic systems where there is energy lost, such as through friction or damping, there may be the opposite, highly organized points and possibly fractal structures. These are infinitely repeating shapes that appear the same no matter how much you zoom in or out. This cool fractal structure is strongly indicative of chaos. Periodic Poincaré maps, on the other hand, would just show single dots as it would only intersect the cutting plane at a few locations. That's a theory. In the digital experiments, I got results similar to what the theory suggested I would find. The periodic pendulum produced singular points on the Poincaré map, and the conservative pendulum had discontinuous unorganized points. In the dissipative magnetic pendulum, there is a more organized pattern, and there is a fractal structure, which is what the literature suggested. Using another method of generating Poincaré maps by sampling the phase space with the same frequency as the forcing, I found results that also replicate theory. These kinds of results where we do some experiments and compare the results to show ourselves how the theory becomes reality. That's what our regular mechanical labs do. And that's what I found that this digital lab was also able to do. So you've seen that Bullet is able to simulate nonlinear chaotic systems accurately. When we analyze the results from these simulations with the same practical methods used in engineering real systems, we found the same results that theory suggested we would. But Blender is not without its limitations. It cuts corners in contact dynamics by approximating contact force as constant over the entire duration of a collision. This is a mechanical experiment I set up, and you can see the trajectories of these colliding spheres are very different between Blender and real life. From these findings, Blender as a virtual learning environment could possibly be used as a digital workspace to introduce new mechanical engineering undergraduate students to nonlinear and chaotic dynamics. In UCD, this could be done in the courses teaching advanced vibrations and applied dynamics. Thank you for attending my presentation. I really appreciate the chance from UL to share my work, and I hope you've learned something new about nonlinearity and chaos from this.
Thank you very much, Aidan, for keeping with the time. Rina just had to leave us now. I'm sure that she was itching to ask you questions on that super impressive presentation. Very well done. Those dynamic images are just awesome. So it couldn't be far from my discipline. So obviously I wouldn't be able to ask you about any particulars, but congratulations on the presentation indeed. I would like to know if anyone in the audience would like to raise any questions at this stage. We just give it 1 minute or two since we're running a bit behind time. If there are no questions, I just wondering, Aidan, if it's something that you are planning to extend this research further. Do you think there's potential there for possible postgraduate study in this area? What would you like to focus on, and how would you develop it?
The focus on this would be for undergraduate students to kind of have a lab in the courses. After my degree, I'm going to be starting an internship in UCD, and I'll be continuing working on this pedagogy to introduce nonlinear concepts.
Super, I'm delighted to hear that you're continuing and that this has been brought forward and bridging that gap with the teaching and this. So there's a lot of work to be done exactly in teaching in the disciplines, and this tool seems to have huge potential.